Sir, excuse me, sir.
Oh, there you go. Can you hear me, buddy? Who was that? Somebody was talking just now. Oh, sorry about that. Just give me one moment. Great. Thank you, Lakshmi. Just give me one moment here. Sorry about the delay. And there you go. Okay. So today, just sharing my screen, guys. Good evening, everybody. Sorry about the delay, guys. By the time I got home, I got stuck on the way, so the delay. So let me come back here. Share the screen. Sharing the screen now. There you go. One more time. Sharing it. Okay. Can everybody see my screen, guys? Quick yes, please. Great. Thank you. Good evening again, guys. And it looks like it is festival time, guys. The next 3 days we're going to be taking a break, guys. Again, we'll be meeting back on Monday. That is just in case I might forget it. I'm just saying it. Due to the festival, a lot of people will be out, so we thought we'll take a break and we'll meet back on Monday. And then I will continue the remaining 3 days on the next week, and we'll try to wrap up next week whatever we can, guys. That is going to be the plan. So with that, today I will introduce you to another algorithm which is referred as Logistic Regression, a very popular algorithm. And we'll try to dig a little bit deep and try to understand that, guys. Okay. So let me see. When you see this picture, what do you see, guys? Let's see. Come here. When you see this picture, what do you see? And let's go back here. There it is. Let's see what you're seeing. Ah, there you go, Priya. Good one there. So there's a heart if you're observing and things like that. Today, we're going to be looking into what is called heart disease prediction, guys. That is going to be today's case study / project. So let me come here, back here. And where is the screen? 8 minutes. Okay. So let's dig a little bit deep and try to understand what is happening. Heart disease describes a range of conditions that affect your heart. Diseases under the heart disease umbrella include blood vessel diseases such as coronary artery disease, heart rhythm problems, arrhythmias, and heart defects you're born with, congenital heart defects, among others. These are some of the heart diseases. Sometimes we keep hearing them, and notice we're all coming from a lot of people are coming from engineering and non-medical background, and yet we are able to talk about these things, guys. Okay. So heart disease is often used interchangeably with the cardiovascular disease. Generally refers to conditions that involve narrowed or blocked blood vessels that can lead to a heart attack, chest pain, or stroke. Other heart conditions, such as those that affect your heart's muscle, valves, or rhythm, also are considered forms of heart disease, guys. And let me see. Heart shape of the heart. Okay. So heart disease is one of the biggest causes of morbidity and mortality among the population of the world, which means a lot of people are dying. It is one of the biggest diseases, biggest causes of the reasons why people are dying for medical reasons. Prediction of cardiovascular disease is regarded as one of the most important subjects in the selection of the clinical data analysis, or more precisely in the medicine field, just like cancer. The amount of data in the healthcare data industry is huge. In other words, we already have a lot of data, and that is what is scenario. According to a news article, heart disease proves to be the leading cause of the death for both women and men. So it is not just women, but also men. About 610,000 people die of heart disease in the United States every year. That's 1 in every 4 deaths. That is the story of United States. Okay. And in India, we also have some statistics and things like that, but this project is more based on US data. And India is just realizing that this kind of analytics and these kind of things are possible. So we are right now getting into the bandwagon where we will be, in a few months to a year, we'll be able to produce this kind of data, guys. Okay. Heart disease is the leading cause of death for both men and women. more than half of the deaths due to heart disease in 2009 were in men. More than half of the deaths, guys, okay? And coronary heart disease is the most common type of the heart disease, killing over 370,000 people annually. Every year, about 735,000 Americans have a heart attack. Of these, 525,000 are a first heart attack, and 210,000 happen in people who have already had a heart attack. So that means that's probably a heart attack a second time or a third time is killing them. So this makes a heart disease a major concern to be dealt with. It is difficult to identify the heart disease because of several contributory risk factors such as diabetes, high blood pressure, high cholesterol, abnormal pulse rate, and many other factors. Due to such constraints, scientists have turned towards modern approaches like data mining and machine learning for predicting the disease. Okay, so in other words, it is not easy to predict when somebody will get a heart disease, what might cause a heart disease and things like that. So that's where humans are failing. Doctors, physicians are failing. What do? We bring in the machines. That's where we can use machine learning. Machine learning proves to be effective in assisting in making decisions and predictions from the large quantity of the data produced by the healthcare industry. Okay, so gentlemen, ladies, that is the context. Everybody with me so far? Cardiac arrest, yes, that is also a very serious thing. My father passed away with a cardiac arrest a few years back, about a decade back, and things like that, guys. But we are all settled now and things like that. So let's get a little bit deep. So that is the context, that is the story or the background where we are coming from. So now let's see what is predictive modeling. We've been already looking at predictive modeling. We've been already doing this one, but let's have another quick look, guys. Okay, build a statistical model to predict the future. We can build a model from the data, and the model can make a prediction whether somebody will get a heart attack, a malaria, cancer, or maybe a COVID. That is what is happening today. Predictive modeling is same as predictive analytics, and these are some of the techniques. Lots of algorithms are there, but these are some of the common, most widely used algorithms. How do we build a predictive model? Predictive model needs two sets of variables: dependent variable and independent variable. Dependent variable is something which is dependent. Imagine a coffee shop. Sales of a coffee shop will depend on the temperature. The temperature will not depend on the sales. Temperature is a process of nature. So sales is dependent variable, temperature is independent variable. It estimate a mathematical relationship between dependent and independent variable means we take the data, we give it an algorithm, whatever result we get is what is referred in a statistical world as a mathematical relationship or a model. That model will help us in making a prediction. Okay, imagine you visit something like Amazon or Flipkart. What are they doing? Every click you make, they are trying to make a prediction whether you're a customer who will purchase a product or not. Okay, and that prediction can be based on your age, your gender, your salary, your marital status. It could be possible that all the females like Reebok shoes, all the males like Nike shoes. So that is what they are using. So the age, gender, salary, marital status, these are referred as the independent variables, guys. Okay, whether you purchase or not depends on this kind of characteristic. Is what it is what it says. Y equals to x plus b, that is the equation of the line. We have looked at linear regression. We'll touch again a little bit of it today. Every time there's a change in an independent variable, the dependent variable changes. If it is a male, maybe they like Nike shoes. If it's a female, maybe they like a Reebok shoes. So the change in the independent variable is causing a change in the dependent variable. So we call dependent variable a dependent variable. As simple as that, guys. I think we may have briefly looked at this one. But let's have a quick look one more time. There it is. So the first phase is understanding the business problem. Imagine you're in healthcare industry and we have just looked at the story of the heart attack, heart disease and things like that. What is going on is a lot of people are dying due to heart attack. So what is that? That's a business problem. That's a problem in the world of healthcare. What do? We translate the business problem into a statistical problem. So we try to understand what can we do. Well, we should try to use a machine learning algorithm. We should try to build a model. But what is the machine learning algorithm we use? Well, that is what is called statistical problem. We're trying to understand which model to use, what to use, and things like that. Okay, so imagine we start with logistic regression. It is one of the things which will help us in predicting this one. And what do? We prepare the data. We try to get the data. We already have the data in this scenario. Sometimes we may not have the data. Now what we do is we identify the dependent variable. The dependent variable is we would be interested, we have a lot of patients. Imagine we have a lot of patients. We would like to predict who, whenever a new patient comes in, if this patient has the characteristics which indicates that he might get a heart disease or a heart attack. So what is that? Whether somebody will get this disease or not is going to become our dependent variable. Then we will identify the statistical method, that is nothing but the algorithm. We can use logistic regression, and then the hypothesis, the predictive variables. Okay, predictive variables is independent variables. Is it males? Is it females? Is it the young people? Is it the old people? Is it the middle-aged people? Those are all the independent variables. Okay, maybe more men are getting heart attacks than women, or maybe vice versa. Maybe more old people are getting, maybe more diabetes people are getting. What are they? They are the factors which are contributing to your heart attack or heart disease. What is that? They become your independent variables. Okay, so what is this? This is called phase 1. You try to understand what is the statistical model you use. Then what do? You take the data. We will do a similar process that we did in linear regression. We will split the data 70%, 30%. So this is where the story of the tutor and the student comes in. We're giving 70% of the data to the student. Then we, at a statistical level, at a mathematical level, we perform univariate analysis, the bivariate analysis, multivariate analysis. We may not have time to do all these things individually because these are slightly detailed, but we'll try to focus more on the model development today. A touch of the other kind of things. So in other words, this is the process where the student is studying. As he's studying, remember the mantra, they are painting a paint in their brain. Okay, then what do we do? Well, that paint is what is the model. That's what we will build. And then what we'll do, we'll test them on the 30% of the data or the questions, which is referred as a validation sample. And then, if we are doing a good job, then we will deploy it. That is called the phase 3. At a high level, this is like a process flow of the building a predictive model, guys. But let's dig a little bit deep and talk a little bit about the logistic regression. Everybody with me, guys, so far? Vaccine now. Yeah, we can definitely use logistic regression for COVID also. So logistic regression predicts the probability of an occurrence of an event. Whether somebody will get a disease or not is yes or no. That's textual data. If you want to predict something like a textual data, we can use logistic regression. It also gives us the probability of an occurrence of an event, which means it can tell you somebody has 80% or 90% probability of getting a disease, or maybe somebody has only 10% probability of getting a disease is what it is. It analyzes the relationship between dichotomous dependent variable and independent variables. Dichotomous means something which has two values, yes or no. So somebody will get a disease, yes or no. So that is called dichotomous. The dependent variable is referred as dichotomous. Okay. And here are some more examples. What is the probability that the debtor will pay the loan? Again, the mantra is to learn to drive a car, you can drive any car. So what is that? If you learn the concept, the data is different, you can apply it on different concepts. You go to the banking industry, you can apply the same algorithm, you can try to predict if somebody will be paying the loan successfully or where they will not be able to pay the loan. And if you go to different industry, maybe telecom industry, customers are churning, means they are leaving the Airtel, they are joining the Vodafone. For some reason, we don't know why. What can we do? We can build a model and we can predict who is the customer who is going to next move away or churn. Will the student pass or fail? We can build a model. Is the claim a fraud or not? What can do? We can build a model. What is that? That is one of the models we can build. It is heavily used in finance, healthcare, retail, telecom, and so on. Almost everywhere and anywhere you will see logistic regression will be used, guys. Okay, everybody okay with this slide, guys? Quick yes, please. Okay, so let's see, take a look at this logistic regression one more time and see what we have here. So there it is. The equation for the logistic regression is similar to linear regression. It is like y equals to mx plus c. That is mx plus c plus some error is what it is. But instead of y, we have log of p divided by 1 minus p. P is referred as the probability. P divided by 1 minus p is the odds ratio. Log of p is referred as the log odds ratio or logit. These are some of the terms that will be thrown around in a machine learning world and things like that. For now, think of them as, like a formula. This is the terminology of the logistic regression, guys. What we can do is, imagine we take the log, we move it to the right hand side, that becomes an exponentiation. We can rearrange this entire equation so that mathematically this is P. This is how you calculate the P. Who does that? That's what the algorithm does, not you. It will use an equation which is similar to linear regression. It is transforming that one into this format at a mathematical level, and then it is using the value of P. That value is between 0 and 1. Probability is always between 0 and 1. Back to school and things like that. This is how it works. And what is this? This is called a sigmoid curve and a S-curve. A sigmoid curve is what it is, like a sine curve and things like that. That is what is the thing which does the magic. So let's go back to linear regression. If you recall, linear regression is, if you want to predict a numerical values, we use linear regression. But if you want to predict a textual value, we use logistic regression. If you recall, in linear regression, we have taken this example of salary and experience. The salary of a employee depends on the experience. So salary is dependent on experience. So salary is a dependent variable. Generally, the dependent variable is displayed on the y-axis and independent variable is displayed on the x-axis. Then take a look at this guy. This guy, let's say for the sake of simplicity, you project it onto x-axis, you project it onto y-axis. Let's say this is maybe 7 years. And let's say the y-axis value is indicating this is maybe $100,000. Okay, so somebody with 7 years is making $100,000. This guy is probably 10 years. He's probably making $150,000 if you calculate. So what is this? This is linear regression. Everything is numeric here. What do we do? If you recall, we have discussed how to draw a line. And using that line, let's say tomorrow we get a new person. He has, let's say, 7.5 years experience. So 7.5 is here. What do? We can project it onto this line and project it here. And we can roughly say what is his salary going to be. So we're making a prediction. This is how linear regression works. What is special about it? The y-axis value is numeric value. The x-axis value is numeric value. But let's say we come to a scenario where the y-axis value is a textual value. It's an action. Action is somebody is visiting Amazon.com or Flipkart.com, and what they are about to do is they're clicking on, they're looking at Reebok shoes, they're looking at Nike shoes, they're looking at Puma, Adidas, and things like that. What's Amazon and Flipkart doing? Every click you make, they're making a prediction. They're trying to predict if you're a customer who's going to make a purchase, or are you not a customer who's going to make a purchase. And imagine, let's take one of the guys here. Let's see, who do we have? Imagine here is Srikanth. Imagine Srikanth is a guy, Amazon, based on his clicks, they're predicting he's going to buy, let's say, Reebok shoes with a 90% probability. What is Amazon going to do? Amazon will not do anything. But let's take another guy. Let's say, come back here. Let's take Madhuri. Madhuri, based on her clicks, the Amazon guys are making prediction that they're only calculating a 10% probability. She's looking at Reebok shoes, and her click data is indicating only a 10% probability. So now what will Amazon do? Well, Amazon will say she's probably going to jump to Flipkart. She's probably going to go to another website. So what is happening? This is called churning. They're losing the customer. So now what is, they will shoot an ad to Madhuri and say, Madhuri, in the next few minutes, if you're going to make a purchase, we'll give you a 25% discount. What is that? Whether she will make a purchase or not is a yes or no. That is an example of an action. Okay. Another example is, imagine a marketing team. They send a lot of marketing emails. And what they would like to do is they would like to understand who are the customers who are going to click that email and have a look at that email, or who are the customers or not. What is that? They click an email. That is also an example of an action. Imagine they send a lot of emails to a lot of customers, and here is what is happening. Take a look at this guy. Let's say, for the sake of simplicity, this guy is 18 years old. What did he do? He did not click is 0. 0 means false. This guy is, let's say, 20 years old, did not click. So all these guys who are on the x-axis here, they have not clicked the email. But take a look at these guys. This guy, let's say, starts at, let's say, 30 years or 40 years. What's happening? As the age is increasing, more and more guys are clicking the email. They're clicking the email. That is what is one. One means true. So what do we have? We have a group of customers who are not clicking the email, and we have a group of customers who are clicking the email. Now, what we would like to do is tomorrow we have, let's say, Srikanth. Srikanth is 30 years age or maybe 25 years age. What is happening? Well, we want to predict if we send an offer to him, will he take the offer? Will he click the email, look at the email and take an offer or not? What would we like to do? We would like to make a prediction. What is a prediction? Prediction is yes or no. What is yes or no? Yes or no is the textual data. What is it? That's where logistic regression comes in. Okay. What is special about logistic regression is at a mathematical level, it follows the principles of the linear regression, which is it will follow the principles of linear regression and come up with the line. That line is referred as the best fit line. Okay. But let's say, come back here. Here is the line. The first step it does is it follows the principles of linear regression. It is coming up with the best fit line. Now what happens is, in linear regression, we were able to mathematically interpret it. We were able to interpret and say, hey, what is the salary we need to give freshers versus what is the salary we need to give for somebody who's going from 3 to 4 years or 4 to 5 years? What does that mean? Well, we are able to make business decisions based on the principles of mathematics. So it was possible. But if you apply the best fit line on in a scenario like this, what is this? There is a problem. What is the problem? Well, the problem is this one. This part of it is a problem. This part of it is not a problem. Okay? If you take this region of the line, we can roughly say, we can interpret this in terms of business terms and say, it looks like as the age is increasing, more and more people seem to be clicking. Pardon me, sorry about that, guys. More and more people seem to be clicking. The email is what we can interpret this. In other words, more precisely, what we are doing is, what I'm trying to convey is, this part of the line seems to be interpretable. But this part of the line, it doesn't seem to be interpretable. We are not able to take the principles of mathematics and we are not able to explain the business. What is that? That is the two edges. So what do? This is what we do. We can convert it into something like this. This is called an S-curve. At a mathematical level, what we can do is the region that we were not able to interpret, we have converted that into this one. We just turned it. And how we'll do that? We'll discuss it. Which means we can now take this region and we'll make an interpretation and say, if somebody is between this age and this age, then what is happening is there are more chances of them clicking an email or making a purchase or taking an action, is what we'll interpret. If somebody is greater than this age, then what do we say? Now we will interpret this and say there is 100% chance or a probability that they will take an offer or they will act. But if somebody is less than this age, what do? There is absolutely no chance. There is a 0% probability they will take an action. In other words, what did we do? We just now translated the principles of mathematics into a business decisions. Everybody with me, guys? Making sense? Quick yes, please. So far with me? Okay. So now, let's say, come back here. Let's take this. How do you convert the best fit line into a sigmoid curve? Well, let's see that. Take a look at this. What's happening is, imagine at a simplistic level, the most simplest example is you take a line. This is the line. You apply a sigmoid function to it, and what does that do? That will convert it into a sigmoid curve. The sigmoid curve is the mathematical mantra of logistic regression. Sigmoid curve. Okay, at a mathematical level, is that one is represented as a mathematical mantra of the logistic regression, guys. So if you come back here, on the y-axis, what we are doing is we are showing what is dependent variable. This is the actual values. And these are independent variable values. So these are the guys who did not take the action. These are the guys who took the action. What are these? These are the actual values. The note is red color. Now, come back here. Take a look at this one. What do? What we are saying is we are going to apply the best fit line. And then we were going to apply what is called a sigmoid function. That is what is transforming it into a sigmoid curve. So now here is a sigmoid curve. Now what do? Imagine we have few customers coming up. Let's say their ages are 20 years, 30 years, and 40 years. Now what can we do? In what way is this curve going to help us? Is what we will do is, if somebody is 20 years old, we can project this onto the curve, then project this onto this one. What is this? This is the value 0, this is the value 1. Whatever this value is, that will become the probability for that guy taking an action. Let's say, take this guy, project this here, calculate the value between 0 and 1, calculate the value between 0 and 1, calculate the value between 0 and 1. What do you do? Well, this is what we get. What is this? This is not what you're doing, this is what the algorithm is doing. Algorithm is calculating the probability values by following these principles. So somebody with 20 years age, they have only 7% probability. Somebody with 30 years, they have 23%. And what's happening as age is increasing, probability is increasing. Okay, what is this? This is P hat. What is P hat? P hat is what is being projected. It is not actual. Notice the green color. Okay, so we're just distinguishing. This is what we are expecting or prediction. Generally, so that is Y hat. Generally, the predicted values are represented with a hat. Red color is the actual value. Based on them, we draw the sigmoid curve, which is the model. We call that as the model. That is the one which is helping us in make a prediction, which is referred as Y hat. Y hat is what your predicted probability is, guys. Okay. Generally, in real world, what do they do? Now, we have seen how we are calculating the probabilities. But what we need to do is we need to convert it into a yes or no. So what do? You establish a threshold. In a marketing domain, what will happen is, imagine a group of emails are being sent to a group of customers. What will happen? Well, they will say, if somebody has a probability which is greater than 50%, treat them as yes. If somebody has a probability less than 50%, treat them as no. So now what is happening? All the customers where the probability is greater than 50%, we have converted them into yes and no. That is how the logistic regression translates them into probabilities into yes or no. Okay, but imagine a COVID scenario. Let us say the COVID is a global pandemic and it's spreading very fast. People don't want to, the healthcare guys don't want to take any chance. In such case, what do? They don't set the threshold at 0.5. They set the threshold much lower. Maybe that is 0.1. So what does that indicate? Now, if somebody's probability is less than 20%, the answer, they're not going to get the COVID. But if somebody's probability is greater than 20%, they're going to get the COVID. What do? Based on scenario to scenario, domain to domain, we set up that threshold. Everybody with me, guys. Quick yes, please. The sigmoid curve is called the model. At a mathematical layer of the model, at a logical level, that is the paint we are painting in our brain for the algorithm, guys. Think of it like that. Okay, so that is logistic regression. That's how it works. Now, back to our data set. Let's see what we have here. Come here. Say, I can open this one as Excel. So let's say, I think I need to open this one. We're looking at folders, our data sets. Say, I think it is, let's run that. And so this is going to be our data. Take a look at this. If you go all the way up, it's starting there. If you come all the way down, looks like we have 303 patients data. No column header. We don't have any columns. We don't know what is column A, column B, column C, and things like that. So notice the last column is generally the dependent variable. 0 means this is a false. 1 means maybe this guy has some chances. 2 means more chances. 3 means more chances probably. That is what we'll try to look and understand. But what is this? This is the data. Ideally, as a data scientist or an AI professional, as an ML engineer, all they'll do is they'll give you data, and they'll give you some brief explanation, and that's all we need, guys. Okay, but let's dig a little bit deep. This data set contains 303 individuals' data. There are 14 columns. Age. What is age? Age is age. Sex is gender. 0 means male. 1 means female. So if you come here, this is the first one probably is age. The second one is the gender. Then come back here. Here's the third one, chest pain type. 1 means typical angina. So take a look at this. This is the one. It's 1, 2, 3, 4. 1 means typical angina. 2 means atypical angina. 3 means non-anginal pain, and 4 is asymptotic. In other words, we're all coming from non-medical background. Most of them, 90% or 99% probably here, are coming from a non-medical background. Yet we are looking at the data and trying to understand a little bit. That is what is the magic of data, guys. Okay. So That is pretty much what we know. Then the next one is resting blood pressure. That is probably blood pressure. It displays the resting blood pressure value of an individual in mmHg. Well, I don't really know what that is, but that is probably blood pressure. Next, move to the next one. Serum cholesterol displays the serum cholesterol in milligrams. So in other words, that is probably related to cholesterol. Maybe serum, here and there, once in a while I keep hearing it. But that's as much as I know. Next, fasting blood sugar. It compares the fasting blood sugar value of an individual with 120 mg per dl. If fasting blood sugar is greater, then it's a true, otherwise false. So let's see what we have here. So there it is, 1 zeros. 1 means probably that guy has sugar, 0 means that guy does not have sugar. Maybe he's not a diabetic. Okay, and next one, resting ECG displays the resting electrocardiographic result. 0 means normal, 1 is having ST wave abnormality, 2 is left ventricular hypertrophy. So there it is, that is something related to ECG. Okay. Next, max heart rate achieved. It displays the max heart rate achieved by an individual. Let's see how that looks. So this guy, his heart, it is maybe reaching a heart rate at 178. I don't know. 178 I think is too high, guys. I think generally 72 beats per second or something like that is what I seem to recall. It's a normal thing, but that is what, again, we don't need to go into the domain of that, but that's max heart rate. Then exercise-induced angina. So this is maybe something related to whether when he doesn't exercise or he does not do exercise, what's happening. Again, something like that. Next, ST depression induced by exercise relative to rest. It displays the value which is an integer or floor. So again, I think these two columns are related to when they're when they're exercising, they're being monitored, and when they're being monitored, they're probably capturing some data. That is what I think it is. Next one is peak exercise ST segment, upsloping, flat, and downsloping. So when you're moving up, when you're moving down, and things like that, something is being noted there, recorded there. Next one, number of major vessels colored by fluoroscopy displays the value. We don't know what that is, so let's see what that looks like. 0, 0, 1, 2, 3, numerical data. Thal displays the thalassemia. 3 is normal, 6, 7 are the, so 3, 6, 7, 3 is normal, guys. And the last one is our dependent variable generally. Diagnosis of the heart disease displays whether the individual is suffering from the heart disease or not. 0 means absence. Wherever you have a 0, this guy did not have a heart disease, this guy did not have a heart disease, no heart disease. But 1, 2 and 3 means 1, 2, 3, 4 means it's present. So these are all the patients who 1, 2, 3, 4, wherever you see, those are the patients who have the heart disease. Everybody with me, guys? Quick yes, please. Okay. Now notice, guys, most of you guys are coming from engineering. I think here and there I'm seeing some bio-related guys. But notice how we are digging into the data of the medical guys. We are suddenly heading into a medical world. So let's take a look and see what is happening behind, guys. Age is the most important risk factor in developing cardiovascular heart diseases, which approximately with a tripling of risk with each decade of life. Can you tell me why age is becoming a major, most important factor in somebody getting a heart attack, guys? Can you think of reason why age is becoming a major factor? What are your friendly thoughts? You don't have to be 100% correct, but just give a friendly thought there. Pressure. Vamsi says it's pressure. With age, your pressure is, your stress is increasing. Okay. Lack of energy. Immunity is reducing. Good answers. Some good answers coming up. So coronary fatty streaks can begin. It is estimated 82% of the people who die of coronary heart diseases are 65 and older. So the more they are getting old, the more they are, the more the chance of getting is what it looks like. The risk of stroke doubles every decade after 55. Decade means every 10 years, your risk of getting heart attack is increasing, guys. Okay. Suddenly we are learning about heart attacks, heart diseases, and things like that. Next one is sex. Men. Sex is gender. Men are at greater risk of heart disease than premenopausal women. Once past menopause, it has been argued that a woman's risk is similar to a man's, although more recent data from the WHO and UN disputes this. They don't agree. If a female has diabetes, she's more likely to develop heart disease than a male with diabetes. Notice that, guys. That's interesting. Some interesting things have been published and observed. Females who have diabetes have more chances of getting a heart disease. Why do you think that is happening, guys? Less exercise. Maybe their nozzles are getting blocked. Interesting. And they are more stressed. Okay, I understand. These days, everybody is getting stressed, not just males or females. I'm sure females are taking up more responsibilities with cooking and also working. A lot of colleagues do that. They keep everyone in the okay. They keep everyone in the heart. Good one there. And bad blood will not go to body. Okay, fitness. They generally are also interested into fitness, so that's maybe the reason. Angina is a chest pain or discomfort caused when your heart muscle doesn't get enough oxygen-rich blood. In other words, blood carries oxygen to the various parts of the body, but for some reason that's not happening. It's causing a lot of discomfort as a result of that. That is angina, chest pain. Next, the blood pressure. High blood pressure can damage arteries. So notice, you're in stress, your pressure will increase, maybe decrease. That will damage your arteries, guys. Okay, something to learn. Then come to serum cholesterol. A high level of low density lipoprotein cholesterol is most likely to narrow the arteries. So in other words, the cholesterol is also impacting. So just be aware of that. We are again not the experts in that, but just a rough look at it. Then the blood sugar. Not producing enough of a hormone secreted by your pancreas, which is insulin, or not responding to insulin properly causes your body's blood sugar levels to rise. So in short and sweet, pancreas control the sugar content inside our body. They generate the insulin, which regulates the sugar content, guys. Okay, that's another one. If you're going a little bit deep, what are we doing? Why are we looking at something like this, guys? We are just understanding a little bit about the data. Now, this is like the data dictionary, and the general understanding is given to us. That is what we generally do in real world. You get a feel of whatever you have, because this is going to be data is going to be your breath. You're going to live. When you wake up tomorrow as a data scientist, what do? You don't think in terms of code. You do think in terms of code, but you will more think in terms of the data. That's why we are looking at the data in a slightly more detail. Everybody with me, guys? Quick yes, please. High serum creatinine. Wow, looks like somebody is into medical here. Some good stuff coming up there. So ECG for people at low risk of cardiovascular disease. They concludes with moderate certainty that the potential harms of screening with resting or exercise or exceed the potential benefits. So something related to ECG, guys. I may not be able to explain that. Max heart rate achieved. The increase in the cardiovascular risk associated with the acceleration of the heart rate was comparable to increase in risk observed with the high blood pressure. So the high blood pressure is also probably causing the heart rate to increase or decrease. That is causing. So notice an increase in the risk of cardiac death by at least 20%. This risk is similar to one observed. So what is this happening? What we are doing is we are trying to understand the story of all this data, why we should build a model to predict if somebody is going to get a heart disease and things like that, guys. Okay, this is all the story which is happening currently, and we can apply this to almost any disease. We can take the data of any disease, we can try to get a feel of what is happening and things like that. So there is again exercise induced angina, pain or discomfort associated with angina, feels tight, gripping, squeezing, and can vary from mild to severe. So both of your shoulders, your back, neck, jaw, or arm, it leaves them in discomfort. So just be aware of that. And exercise, treadmill, ECG stress. So generally what happens is patients are asked to walk on a treadmill, and then as they're walking on the treadmill, they're connected to some devices, the sensors and things like that. They generate the data. That is probably what is being explained here, guys. Gentlemen, ladies, that is the data. Now let's get into a little bit of action. Everybody with me? Quick yes, please. Lose strength after some age. I see your point. As we get more and more age, we lose that resistance, our immunity, all those things are decreasing. That is also a good point, guys. So let's come back here, and let's get back to a little bit of code here, guys. Okay, so I'm going to start with, I will tell the Jupyter to point to this particular directory. This is where I have saved our file. tested this before. So CHDR, we're telling, hey, Jupyter point to this directory. And the next step is we're going to read this file. Before that, we'll do some imports. These imports, I will not explain everything, but some of them may be unnecessary here. Warnings will just clear the warnings and things like that, guys. Okay. So if you recall, read CSV creates a data frame. We discussed about data frame. Head will give you the top 5 rows. So let's see how that looks like. There it is. That's our data. Head, we are only looking at all the columns and only the top 5 rows. Okay. Then come down here. We're going to give them some column names. Imagine these are the column names. We asked our physician or somebody, and they said, hey, this is what this is. We're giving some of them short names: age, sex is gender, CP, that is blood pressure, thalassemia, something like that. Here's the ECG slope, and target. The last one is target. Generally in a Python machine learning world, the target is nothing but the dependent variable. Okay. So those are the columns. Then again, we'll verify how with the column names our data looks like. That's how it looks like. So notice here what's happening. That's the target. 0 means this guy does not have heart disease, but 1, 2, 3, 4 indicate they have heart disease. Now what is happening? We only took 300 patients data. In the real world, 300 patients is like a drop of water. We will have a lot more data and things like that. And what's happening? Well, this guy is 63 years old. He's probably a male. This is his CP, test BPS. You look at these things, and what you're observing is he didn't get the heart disease. But let's say take a look at this guy. This guy is also similar. He's similar to the upper guy. He's slightly more here. Similar. Everything is, let's say, similar. What's happening? He got a heart attack. Now imagine what's happening is everything is same here in this row. So in other words, let's say come back here. Put this here. For the sake of simplicity, let's say here's the first patient. This guy, he did not get heart attack. He's good. He's good in health. But let's say take this guy. Let's say for the sake of simplicity, he has almost exactly the same characteristics of the above. For the sake of simplicity, almost same you assume. But what's happening? This guy is not good. He got heart attack. So now if a physician looks at a couple of patients like this and is trying to understand why this guy, these two are similar, but this guy did not get it. Or this guy did not get it, but this guy got the heart attack or heart disease. What's going to happen? Well, that's going to be a very difficult thing. Looking at two patients, you're trying to make a decision. A physician may not necessarily be able to answer it, especially if these values are very, very close. And looking at 300 patients like that is super complex. Your head will hurt, your brain will hurt, your eyes will hurt, you will feel like running away, you don't feel like doing this job. That's where humans fail. When humans fail, what do? We bring in the machines. Everybody with me, guys? Quick yes, please. Okay, so it is not possible for humans to look at 300 patients like that and try to understand what are the factors, what are the characteristics. Whether you're a physician or super physician, it is not possible, guys. 300 is very, very small amount of data in the real world. Okay, so what do? That's where we are bringing in the machine learning. But before we build a model, let's do some basic pre-processing, data cleaning. So notice is null. You ask the data frame, are there any null values? Notice there are a couple of columns. It looks like only these two columns have some null values, which means there is some missing data. Okay, so let's say, what do? Here's the target. Target is unique. And what we are going to be doing is 0, 1, 2, 3, 4. 0 means all the patients with the 0 do not have heart disease, but these are the patients who have a heart disease. So this is like no, this is like yes. All these are yes. Okay, so now what we are going to do is, notice we're going to run this target.map. Wherever there's a 0, put a 0. Wherever there's a 1, 2, 3, 4. Wherever there's a 1, put a 1. Wherever there's a 2, put a 1. We're using a dictionary and we're doing a map. And if we do this and run this and check for the number of unique values, now notice it becomes 0 and 1. What was 0, 2, 1, 3, 4 has now become 0, 1. In other words, wherever you see a 2, 1, 3, 4, we are replacing that with a 1, and a 1. Everybody catching that, guys? Quick yes, please. Okay, so let's say, go one step ahead, come here. Let's see what is the sex of the gender. Okay. We should probably see a 0 and a 1. What we'll do, we will come back here. Oops. We will go ahead and convert that to 0 to female and 1 to male, and then check the unique values. So we're converting numerical data into textual data. 1 is male and 0 is female. The map, that is what it's taking a dictionary of a key and a value. We discussed about a dictionary, and for now think of that as how map is working, guys. It takes a dictionary and substitutes the values. Then come to a column called thalassia or something like that. There are two missing values. What we will do is we'll do a fill NA. We're saying go to this column. What you do is you calculate the mean, average of that column. This will calculate the average of that column. Fill NA means fill null values with whatever. Wherever you see a null value, fill it with a mean, and then you check again if there are any null values. What do you do? Well, that's a simple technique. There are a lot more techniques. These techniques based on may change based on scenario and domains, guys. So this is like a globally commonly used scenario. So now what is happening? We filled it up. And if you're asking it, hey, are there any null values? It's saying 0. Okay, we will also repeat that for CA. I don't remember what that is. Let's say, see how many values are null. 4 values are null. Repeat the same. Fill them with the mean for the sake of discipline, simplicity, and there it is. We filled up the. So this is a touch of data cleaning, guys. Next, let's move to the next column. Let's see what it is. Now here's, maybe I think this may not, let's see. We'll try to do the plotting here. Look at this, set context. Give it a moment. It's going to be, I think, a little clumsy here. I think a lot of overlap of x-axis is happening. I need to set the things here. The blue color indicates, these are the guys, the blue color indicates they don't have heart disease. The orange color indicates they have heart disease. In other words, let's say, come here. This is like a bar chart, a vertical bar chart. What's happening? Majority of the guys who seem to be having heart attack. And I think, if I increase the size of this one, we'll be able to locate the age. Let us say that is, let's say 58 years. Around 58 years. Okay. We are having majority of the patients who seem to be getting heart attack, and then after that the number of patients is decreasing, and here it's increasing. As you're reaching towards your 50s, your thing is increasing, and again it's decreasing. So we're kind of trying to tell a story, observe something here, guys. There's again, we have ways how we can increase the figure size and things like that, but again I will not go into those aspects now. Let's also do a cat plot. Cat plot is like a category plot, which is like a textual data and things like that. So there it is. So what do we have? We have now, one of the columns we have is male and female, and here is the age. Okay, take a look at the oranges. The male guys, we are close to, how much is it? Let's say 55. At 55, a lot of the people, or in other words, more precisely, the age is 55, and we are seeing a lot of guys are getting a heart attack, and this is slightly higher, which is close to 60. More females, they are at the age of 60, they're getting a heart attack. That's what that is showing. So let's say that's x-axis, y-axis, and so that is the x-axis gender, y-axis hue means color. So distribution of the age versus gender roughly is what I'm able to translate it, guys. If I spend a little bit of time, I'll be able to explain it a bit more, but for sake of simplicity, my objective is not to teach not go too much into visualization aspects right now. I'm going to put back female as a 0 and male as a 1. Why? Generally when we build a model, we don't give textual data in our data frame. We have everything as numerical data. Just for visualization purpose, we did the reverse. We converted 0 to female and 1 to male. So I'm putting it back to its original values. Then now this is where the action begins. Generally, to build a model, what do? We have to separate the dependent and independent variables. So you go to your data frame, the subsetting, take all the rows, ILOC if you recall, except the last column, just the target of the dependent variables, convert it to a numpy array. And there is why. So this is where we separate the dependent and the independent variables. First step is separate the dependent and independent variables. Now this is a function train test split. It is doing the unpacking, which is separating the training and the testing. 80%, 20%. So let's run that. So that is 80% of the questions, 20% of the questions, 80% of the answers, 20% of the answers. Okay. Then what we'll do, we're going to scale the data. In other words, let's see if we say x underscore train, x underscore train, see how that looks like. This is roughly 80% of the rows and columns. And more precisely, let's scroll up a little bit. If you look at our data frame, notice the column age is in units of 10. The gender CP is in units of units. This is in units of hundreds, and units of hundreds. And if you go here, some of them are in single units, some of them are in tens and things like that. Now we can take this data and give it to an algorithm, guys. This is a slightly advanced topic. Maybe I might confuse you a little bit. So now what will happen if all the columns are in different units is an algorithm may end up thinking that age is more important because its values are higher. This is even more important because its values are even higher, and this is more important. That is called being one-sided, being partial, or being biased. Okay, what do? We should not try to have any, that is called mathematical bias. There is bias. If a algorithm thinks that a particular column is important, then when it builds the model may not do right predictions. So what we should try to do is we should try to scale the data. It is a technique called pre-processing. So notice x underscore train. If I run this one, we're creating an object of standard scaler, and you say fit. Remember, in Python machine learning world, you'll call fit a lot. So let's say come down here. And now if you look at this, what is standard scaler? This standard scaler, what it is doing is it is taking each column. It takes each column. It is subtracting. It will calculate the mean, subtract the mean, and divide by the standard deviation. Mean and standard deviation. That is called standard scaling. So now what happens as a result of that is almost all of the columns, their units are coming to the same scale. When their units are in a similar scale, maybe between -2 to +2, -3 to +3, and things like that, an algorithm will not be biased. What is this? This is removing the mathematical bias. It is something that you need to manually remember for now. Everybody with me, guys. What are these? These are generally the common techniques that we do before building a model. Okay, so that is what is called a step of pre-processing. We have to repeat that for about 20% of the data also. And I spent some good amount of time how to split the data, why to split the data earlier, guys. So there is x underscore test. Now what we do is take the data. We're going to import Logistic Regression, which is a class. We're going to create an object we're going to call a fit. So this is where we are taking the 80% of the questions and the 80% of the answers. And we're going to give it to our student, who is an object of Logistic Regression. When you say fit, what is happening? This is where our student is studying painting a painting in his brain. So now what do? You go ahead and you say predict. X underscore test is 20% of the questions. You say predict them. And if you look at y underscore pred, these are the predicted values. It's predicting somebody is 0 means no. 1, 1, 1, 1 means it's predicting yes. So what do? Instead of looking at multiple of them, we look at what is called confusion matrix. And let's see how the confusion matrix looks like. So now this is a slightly deep topic, tough topic. I will probably spend a little bit more time, maybe in the next session, guys. But I will try to give you a brief explanation of this and see what this is. Put this here. So this is referred as a confusion matrix. And what we have is, think of, for the sake of simplicity, let's say, these are what our predicted values are. Predicted values. And we'll say, here are the actual values. We'll put actual values here. So let's say, predicted here. And let's say, let me select this. I'll put actual. So predicted is, let's say, come here. These are 0 and 1. on there. And actual is, let's say, come here. We'll put a, oops, one more time. Select this, a 0 and a 1 here. This is referred as a confusion matrix. As the name suggests, it is confusion matrix. Okay, and probably in the next session I will give you a bit more, but let me try to see. So what is happening is 31 patients, based on our predictions, what is happening is 31 patients are actually 0. 0 means in a healthcare world it's negative. They're actually negative, which if they're negative means they're healthy. They don't have a disease. And what is our model predicting? Our model predicted as 0. Predicting 0 as a 0 means this is called true negatives. Why? What our model is predicting is negative. Okay, this is negative, and what's happening? Our prediction is true. So this is called true negatives. What is this? This is true negatives. And come back here. Let's say choose this one. Come to 9. What is 9? 9, they're actually 1. Means there are 9 patients who have a disease. What's happening? Our model is predicting as a 0. Which means these are incorrect predictions. So what is happening? Our model is predicting as negative. 0 means it's predicting as negative. And what's happening? Our prediction is false. So we call that as a false negative. Okay, then come to 4. So 9 patients, they actually have the disease and our model predicted incorrectly. Then come to the 4. 4 is, what's happening? They are actually 0. Okay, they're actually 0, which is negative. Our model is predicting as 1 means positive. So what do we say? We say our model is predicting as positive, but they're actually negative. So what do we say? This is our prediction is false. These are called false positives. Then come to 17. Let's say choose this one. So here is 17. 17 of the patients are actually yes. 1 means they are positive. And what's happening? Our model is also predicting as positive. So what is that? Our model is predicting as positive and our predictions are correct. They are called true positives. Okay. Now what is the catch here? The catch is the left hand side diagonal, the true negatives and true positives is the correct number of predictions. That is called accuracy. Whereas this one, let's say come here, choose this one. The right hand side diagonal is the wrong number of predictions, false negatives and false positives. 9 patients actually have the disease. And what did our model predict? Our model has predicted as no. So imagine there is a patient, our model has predicted you're going to be okay. And what is happening? Well, these guys are getting the disease. That's a dangerous scenario. Okay, 4 patients, what's happening? These are false positives. Our model predicted as positive. Okay, positive means 1. So now, what happened? Well, if you think your model is indicating a patient is going to get a disease, what will a hospital do? Well, they will ask them, hey, why don't you get some tests done? And what will happen? Those guys will spend some money. They'll get some tests done. What is happening? Nothing is happening. No, so that is okay. In other words, in certain scenarios, false negative is more dangerous. In a certain different scenario, false positive is more dangerous. What is this doing? This is called a confusion matrix. This is one way to understand how our model logistic regression is performing. Okay, so let's say how to measure if a model is working well is probably what my task, what I will be explaining in the next session, guys. But let's say come here, take a look at this one more time. Here is accuracy for, let's say, testing set. Let me run this one. This is nothing but the left hand side diagonal 78.6, that means roughly 79%. Accuracy 79% means for every 100 patients our model has been predicting correctly for 79, close to 78 or 79 patients. That is what the accuracy means. Everybody catching it, guys? Quick yes please. Okay, so what is that? We use a confusion matrix to understand. Confusion matrix and accuracy are referred as the performance metrics. After we build a model, generally what will happen is you go ahead and give this model to your healthcare organization. You tell them, hey, start using this model for making predictions. So as the patients come in, they're using this model. And they keep in mind that roughly out of every 100 patients, 78 patients, you are probably going to be predicting correctly. Now, behind the scenes, what we will do is we will go back and try to refine our model. That is slightly beyond the scope of uh, these sessions, guys, but we try to increase the accuracy of these models. This is what we will be doing as data scientists, ML engineers, and AI professionals. Everybody with me, guys. Quick yes, please. Okay, in the next session, my plan is I will go a little bit deep into confusion matrix, explain you some more performance metrics and things like that, because that is the life cycle. Once you build a model, you try to improve it, you try to understand it, look at it from multiple ways, and try to get a feel of it and understand it in the coming up days, guys. Okay, so that is going to be next one. The next session, because the next 3 days everybody is going to be in probably traveling and things like that, guys. So we're going to be taking a break. We'll meet again back on Monday, and we'll continue our journey from here. Everybody okay, guys? Today's thing, is it helpful? Is it giving you an idea, guys, how things work and what you do and things like that? Cool. That's what will see. Feature engineering is a short answer, just one. And okay, so these are the kind of things that you will be working, guys. That's what I want to give you. If we have more columns also, should we write each and every column? You generally have the data, Santosh. You don't write it, but you are given the data. Cool. Okay. Syllabus copy. Okay. Can we write the exam without the material? Okay. Points taken. We're working on it, guys. Yeah, the code I'm going to be sharing, I already shared the code till yesterday. So today's one, I'm yet to share it. Okay, good. Thank you, Pujita. Yeah, wish you all a happy Sankranti. And Bhogi and Kadama also, guys. Okay, good, just one. Thank you. And let's see any other questions, guys, before we wrap up today. We'll take about a few minutes here. If it is shared, yesterday's code, I see. I think association rules mining, I did not share it. I think I shared up to clustering, guys. Sorry about that. The same link, guys, that I have shared earlier, it will be put on your, YouTube sessions and things like that. Great. Happy Sankranti, happy Pongal, guys, to all of you. Thank you again. Wish you all good holidays. There you go. Thank you, Hemant. You're a sportsman, buddy. I appreciate that. I was just looking for that. We will apply to other organizations. Yes. The similar kind of concepts we will apply in other domains, guys. And link materials, I think somebody shared the link, guys. Please look in the chat window. You'll be able to find it. Thank you, Madhuri. I appreciate that. General doubt to put the data scientist. If any individual chooses to take up the data scientist profile, how deep is knowledge of the different domains expected? No. Ravi, you are not expected to be a domain expert. Domain expertise is something which you will learn on the fly. What mainly you will be expected is how to use the algorithms, when to use the algorithms, and things like that. If you know how to use the algorithm, it's like knowing to drive a car. In which road you will go, that is what. Every domain is a different road. One is going from Hyderabad to Vijayawada, another one is going from Hyderabad to Chennai, another one is going from Hyderabad to Bangalore. So Hyderabad to Vijayawada is your healthcare, to Chennai is your telecom, to Bangalore is maybe banking domain. What you need to know is you need to learn how to drive the car. What is learning how when to use which algorithm, where it will work, how it will work is what is the understanding that you need to have, Ravi. Data analysts generally don't do the predictive analytics part of it, but they only perform the data cleaning, data acquisition, data cleaning, and a little bit of visualization. They're not involved in the modeling part of it. A data scientist is complete. We have a touch of data visualization, data cleaning, and also the modeling is the most important. That is the heart of a data scientist. But again, we spend more time in data cleaning and data pre-processing is what it is. Data modeling is the last 10 hours of the match. The first 40 hours of the match is the data pre-processing, cleaning, and everything. Domain knowledge will help to some extent, that is true. So, but again, nobody can understand the complete domain. To play cricket, you don't have to learn the complete cricket and play cricket. You play cricket, learn cricket, and play cricket. As simple as that. The GitHub link, the Santosh or somebody, can you post that link? There you go. Hemant, you're a sportsman, buddy. I appreciate that. Keep it up. Thank you. Tab 9 auto completion tool. Srikanth, I don't know about that, buddy. I have not really used it. I'm hearing it for the first time. Okay. Okay, guys. You guys take care, and I'll be wrapping up this session today. The next session is going to be on Monday, guys, due to the holidays and everybody is going to be out of town. Happy Pongal, happy Sankranti to all of you. Andarki Sankranti Subhakangshalu. Have a good one, have a blessed one. Stay safe and keep learning. Thank you, guys. Signing off for today. Bye for now. Dhanyawad.